Hi, my name is Nick, and today we're going to talk about a little normal shock problem that I want to take a look at. And I've been out of school for a little while now, but I remember there not being a ton of useful resources once I got past a certain point in school, at least that were like high quality and that I actually felt like watching. And just, were simple like this, right? Just attacking a problem, kind of how an engineer would think through it. And, because that's ultimately what's important on an exam. So, obviously, it's a very simple and kind of easy problem, but nailing down the stuff like this, like the fundamentals, is really key to understanding those more complicated problems. So let's go ahead and get started. I'll read the problem statement and we can take a look. So we got a helium flow with a velocity of 2,500 meters per second and a static temperature of 300 Kelvin that is passing through a normal shock. We want to determine the helium velocity and the static and stagnation temperatures after the wave. Assume helium to behave as a perfect gas with gamma of 5/3 and a gas constant of 2077. So real quick, I know it's simple, but we're going to draw it anyway because that's what engineers do. All right, you got our normal shock. We got V1 of 2,500 meters per second. Static temperature 1 of 300 Kelvin. And we're looking for V2, T2, right? Stagnation or static, and our stagnation temperature. Okay, so pretty simple problem. We'll go ahead and get gamma. So gamma is 5/3, but that's 1.67 if you divide that out, just so it's easier to use to plug into a calculator. And we'll go ahead and write out R, just so we've got everything kind of where we want it. All right, so this is pretty much set up now. So kind of general flow of problems like this. Specifically on this one, you want to go ahead and get Mach number on the left side of that shock, right? And then you can go ahead and use either the compressible aerodynamics calculator that I'm going to use today. I'll go ahead and put a link to that. Or you can use tables. I would definitely recommend, if you don't know how to use tables, I would start learning how to use those. Because you should absolutely use the tables before you go ahead and use some quicker tools like I'm about to today. If you'd like to maybe learn how to use those tables, I can make something on that too. It's pretty easy. We can walk through it. But just for today, because this is not a problem on how to use tables, this is just a normal shock problem, I'm going to go ahead and skip that today. All right, so let's go ahead and get started. So let's go and find Mach number, right? We've got a gas constant, we've got a gamma, and we've got a static temperature on that left side of that shock. So we can go ahead and get the speed of sound there, right? Using our little A equals gamma RT. It's a bad R right there. Right? Right, and that will give us, let me see what that is. So we got 1.67 times 2077 times 300, and we'll square root that. That gives us about 1020. Call it 1020.09. Okay, so now we've got velocity of our actual gas compared to the speed of sound. So I'll write it out for us. Okay, so we've got 2,500 divided by 1020.09. That gives us a Mach number of 2.45. Okay, so let's go ahead and add that back to our drawing up here. Okay, so at this point, you're going to go to your normal shock tables. I guess in this case, right, since we've got a different gamma, you'd have to use either a calculator or use your use the actual like hand calc formula there. So in a test setting, right, where you don't have access to like the online calculator, I would use the formula sheet in this case. But since we're not in a test setting, we're going to go ahead and cheat and use the online calculator, right? So we've got a Mach of 2.45. So let's go ahead and start with, we'll start with getting T2, right? Just the static temperature. So from our normal shock tables, we've got T2 over T1 for this particular Mach number of 2.719. We'll go 2.719.5. We'll go 4 decimal places. Be real precise today. So that gives us a T2 of 2.7195 times our T1 of 300 Kelvin. Get my little calculator going. 2.7195 times 300 gives us 815.85 Kelvin. Okay, so here's part of our answer. And just a little like intuition sniff check that we could do right here, right? As we pass through a normal shock, think about what's going to happen, right? So certain things should happen to your flow as it's passing through a shock, or as you go to the other side of a shock, right? So in this case, what should happen is V2 should be lower than V1, right? Because your flow is slowing down as it goes through a shock. T2 should be higher than T1, and your T02 should be lower than T01. I know we don't have that, but if we wanted to, we could go back and look at it and just kind of like sniff check our answer. Anywho, let's go ahead and continue with the problem. So we've got T2 nailed down. So if you wanted to get V2, we can actually just grab M2 from our table here. So from our table, we've got, oops, I'm going to go add that to my diagram up here. M2 ought to be 0.557. So that confirms that our velocity will have gone down, right? Or after we go ahead and get speed of sound, it will have gone down. So we've got, what did I say for T2? 815.85 Kelvin. Okay. So you can kind of see where I'm going with this a little bit now, or I hope you can, right? So we've got a temperature, a static temperature on the right side of our shock now. We've got gamma and R. That means we can go ahead and get speed of sound again, right? So we have A2 equals, call it 1.67 times 2077 times, it was 815.85. Okay, so A2 in this case is 1.67 times 2077 times 815.85. And then we can go ahead and square root that. Should get 1682. Oops. 0.22 meters per second is our speed of sound there. And so at this point, right, we've got right, so solving for V2 here, we've got V2 equals 0.557, right, that's our Mach number, times our A2 is 1682.22. So we got a V2 of 936.99. We'll call that 937. We're engineers here. We'll call that 937 meters per second. Okay, so there's V2 nailed down. Sorry for, taking time to do the math kind of off screen here. Kind of the way, I'm just going to keep talking as I write here. Kind of the way I want these to go if I continue to make them is just be sort of like very informal, like just first glance at a problem, kind of talk my way through it and hopefully kind of share some of the intuition that I come across as I go through a problem. So last thing we want to get is we want to get that T naught 2. Right, so we've got a T2 and we got a Mach number. So we can go ahead and go to our normal shock, or not our normal shock, our isentropic flow tables. Oops, 0.557. We'll go ahead and calculate for that. Okay, so from our isentropic flow tables, sorry, using a Mach number 2 of 0.557, that gives us a T over T naught of 0.9063. Okay, so we've got T2, we don't have T naught 2. We'll go ahead and sub that guy in. I think it was 815.85 Kelvin, if I remember right, over 0.9063. I think that's right? 815.85, yeah. That'll give us a T naught 2 of 815, whoops, type it in my calculator here. 85 divided by 0.9063. That gives us a T naught 2 of 900.2. Yeah, we'll call it 0.2. All right, and at first glance, this pretty much passes the sniff test, right? So we've got a T2 that's higher than T1, right? Flow is slowing down, so your temperature is going to increase with that. Same thing with velocity, right? Velocity's lower than our V1. Mach 2 is lower than Mach 1. And also you've got, just at initial glance here, I know I'm pulling directly from tables and doing simple math, right? But you always want to kind of do something like this, right? Don't just trust whatever comes out of your calculator, right? This kind of happened to me like in the workplace when I first became an engineer. I was trying to be fast and trying to get stuff to my bosses quick, and like I did not do an awesome job of like checking my work before I gave it to them. So definitely avoid doing that, and like get out of that bad habit in the classroom setting before you get to work. I've worked my way out of it now. But yeah, I mean, that's pretty much it. Obviously these problems are going to get more complex, but just like these fundamentals are the kind of thing that you don't want to be screwing up on later down the line when you get to those harder problems. So I think that's all I've got. If you'd like to see more, definitely let me know. Any topics, I really enjoy like the fluids, thermo, aero stuff. But if you want like statics stuff, if you want like mechanics and materials stuff, I could probably review some of that and help you out a little bit. But I think that's all I've got. So appreciate you checking me out.